Final question. So we've got a little proof to begin with, and then this one is saying, well, there's a differential. Tell me why in terms of x. So it's like saying undo your differential, i.e. integrate. So a little proof and then integration. So let's start with our proof. I put some of our formulae on the side, and the only one that isn't here is that tan x is sine over cos. That is National 5, so you should remember that. And the only other one that's also not there is that sine squared x plus cos squared x is equal to 1, also National 5. So again, when you go in, you write them down right away if you're worried you'll forget them, or even just to remind yourself to refer to them. Okay, so let's try and prove this then. So 2 tan x cos x. So I would say that's going to give me 2 sine x over cos x. And in fact, I'll put that in a different colour. I'll just put the 2 in a blue. So I've now substituted in for tan x. And then I've got cos squared x. So what's that? This is my left hand side. So what's that going to become on the next line? Well, I can cancel out a cos from top and bottom. So that'll be 2 sine x cos x. If I just cancel out a cos and a cos, just one of them. And if I look over here, that is the same as sine 2x. So that's then equal to, not 2, sine 2x, which is equal to the right hand side. Not bad for 2 marks, not bad. So please, don't be scared of these. They're nice little questions, but you do have to remember these original rules from last year. Okay, and the marking scheme looks like it's saying you have to, write that out properly. You can't just, skip ahead or anything. So maybe just to be on the real safe side, you could write what you're using on the side. You could maybe even say tan x is equal to sine x over cos x, just to keep your marker happy. And then here you could be saying that sine 2x is equal to 2 sine x cos x, something like that, I don't know. Just to show what your method line, just to show what you're thinking. Part B. Let's have a look, see if I can find some space over here. So for this one, I'll move over a little bit. So I just thought I'd put these here just to remind us of our identities we're given at the front. Okay, and all this is saying is when I differentiate, you multiply by the differential, and when you integrate, you divide by the differential. That's pretty much all it's saying. Okay, so let's have a wee think about this then. So I'm saying that dy by dx, I can already see me running out of space. I hate when this happens. I'm just going to take them out. Yeah, so dy by dx is equal to 6 tan cos squared x. Okay. Very good. And I'm going to try to express that in terms of y. So I'll need to integrate that with respect to x. Now I know that 2 tan x cos squared x is equal to sine 2x. Okay, that's, look at it, given that as a clue. I know that I've got is equal to sine 2x. I've just proved that. So what's the difference then between this function and this function? Well, it's been times by 3, hasn't it? So then that's what it's saying, tan 6 tan cos squared x is surely then equal to 3 sine of 2x. So if I want to integrate that, I'll be saying, well, I'm going to then do the integral of dy by dx of 3 sine 2x dx. Because it follows that that's just multiplied by 3, so I've multiplied that one by 3, so I'm just substituting in this for this. And this is something I can integrate. I can't integrate complicated functions for trig, and chain rule and stuff breaks down, so usually it'll be in this kind of form here. So let's have a look then. What's this tell me if I integrate? If I integrate sine, I get negative cos. So I can right away say, right, I'm going to have negative cos, and your bracket always stays the same. Right? And this is saying you're going to divide by the differential of your bracket. Now my bracket's 2. So the 3 stays where it is, and I'll just put this in a different colour. I'm going to divide by the 2. Yeah? And I don't have dx anymore. I've got plus c. Remember, your dx, it's almost like it turns into plus c. Okay, and that is us finished. It's not asked us for any. Oh no, sorry, we're not finished. We've now got y is equal to that. Almost finished. We need to get rid of the c, so we need to substitute in when x is 0 and y is 3. So when x is 0 and y is 3, we get negative 3 over 2 cos, yeah, I'll do a bracket. Cos of 2 to the 0 plus c. So let's solve that then. What happens, what's cos when it's 0? So you can put it in your calculator if you want, but we shouldn't have to. So cos when it's 0, let's have a look. At 0 degrees, it is equal to 1. So that's going to come out then as 3 is equal to negative 3 over 2. Because this bit, that bit here, just becomes 1. And I've still got my plus c. Very good. And I think I'm just going to put this into halves. So I'm going to say that's 9 halves. Not 9 halves, sorry, that would be thirds. 6 halves. Negative 3 halves plus c. So that means that c has to be equal to 9 halves. So my final answer is going to be y is equal to negative 3 over 2 cos 2x plus 9 over 2. Nice little question. There's a few little twists and turns in that at the end. In a way, it's drawn on a little bit of reasoning here, for example, to understand that this function is similar to one you've got, but you have to times it by 3. Then you've got to use your composite function trig to integrate it. And then you're saying, well, I need to remember what the c, I need to remember solving the c, which I nearly forgot about. I nearly thought, oh, that's me done. So you get your c at the end. And at that point, you do have your calculator, so you can just toggle that in if you want. But actually, if that was a non-calculator question, you would have had to say, right, well, what's cos when it's 0? Multiply this out, and then rearrange. So a wee bit in the end there. But for your 4 marks, you're getting your first mark for this bit here. So just 3. Then you're getting a mark for this, or 2 marks for this bit actually. Yeah, and you're only getting 1 mark for the C. So actually this little bit in here is the absolute key bit in here. Okay, understanding what you're integrating and making sure you integrate the 2 parts and remember your C. So very, 3 marks for in there. Pretty good, eh? Pretty good. So that's the end of the paper. I chatted through the paper at the beginning. The very first video, so if you're interested in a quick, run down memory lane, you're welcome. But yeah, there was some integration, some differentiation, there was a fair bit of trig, there was an optimization question, wasn't any logs in this paper. And like I said, I really do think when you're deciding what to study, your straight line stuff should be really tight. I think the reverse chain rule and the chain rule, that's very similar each year. I would make that tight. Your wave function is a complicated bit of work, but it's very similar every year. So I'd get that recipe nailed as well. Your integration is a bit tricky. I think the last bit is the worst bit. Getting your setup is where most of the points are. So remember your dx. Remember the rule. Add in 1 and then divide. We had our optimization question. Miss out that first bit, but the last bit, equations, stationary point, nature, answer. Just take your time with it. Solving trig functions. Don't forget to add on or take away even your period if that comes up. I thought the graph question was pretty fair. The roots are the turning points. That's your main bit to remember there. And at the end here, with a little identity question, you need to remember tan is sine over cos, and I'll just quickly write that in because that's now gone. You'll need to remember that tan x is sine x over cos x, and that sine squared x plus cos squared x is 1. If you remember those two, you're not given them, then that'll be really helpful. Okay, so yep, pretty fair paper. Hope that was helpful, and yeah, best of luck.